Hello, my name is Ghislain de Joussineau, and I'm the Director of Technology and Operations in BICIP Lab. By background, I'm a structural geologist, and I have been working on fractured reservoirs in the last 20 years. And this is the subject of our talk today. All right. So the subject today is naturally fractured reservoirs, our experience and workflows to maximize the value of these very particular assets. This is the outline of the talk. I will say a few introductory words and then describe the workflow and tools that we have put together for these very specific reservoirs and illustrate that with a case study. So fractured reservoirs are specific in many ways compared with classical matrix reservoirs because they have specific production mechanisms and associated issues. For instance, fractures can provide very good permeability and well productivity, but this could be very local effects with lots of heterogeneity. And that's the second point. It's very typical in fractured reservoirs to have an extreme heterogeneity between the matrix that provides the storage through the porosity and the fractures that provide the permeability with very limited storage. Because of this very high possible permeability, fractures also cause a high risk of early gas or water breakthrough in the reservoirs. And last but not least, as I mentioned, they have very different flow mechanisms compared with classical reservoirs because in fractured reservoirs, the viscous flows don't work well and we have to rely on capillarity and gravity much more than in classical conventional matrix reservoirs. So we have to design a good recovery technique to get the optimal production in these reservoirs. In terms of challenges, it's particularly complicated to characterize and model fractures for many reasons. First, it's difficult to detect fractures in the early life of a field because you may not see directly from the beginning the impact of the fractures on the production. Of course, it's also difficult because there is no direct way to measure the key parameters that are the fracture porosity and permeability. You could do that with matrix, with rocks, using logs and cores. You cannot do that with fractures. You have to design an indirect way of assessing the value of these parameters. Again, there may be very little data available for fractures. For instance, the image logs are key data for fractured reservoir studies. They are not typically acquired in every well in the reservoirs. And finally, the study of fractured reservoirs requires different methodologies and tools than those used in classical matrix reservoirs. And this is something I will describe later on in the presentation. So we need a dedicated approach because we have very specific features in fractured reservoirs. In the IFP Énergie Nouvelle group, to which we belong, we have a history of more than 30 years of research on fractured reservoirs, the fracture modeling, and the fracture simulation. So this huge experience developed in all kinds of contexts allowed us to build a consultancy group dedicated to fractured reservoirs 2 decades ago. And this group is composed of structural geologists, geophysicists, and reservoir engineers, because as I will show, integration is the key to tackle the challenges of these reservoirs. We benefit from a worldwide experience that I will quickly describe as well. And many of our studies have been the subject of publications that you can find in international conferences like the SPE, for instance. And last but not least, in our workflows and in our studies, we use the technology that has been developed at the IFPEN, and then I will come back to that also. FracAFlow, which is our powerful tool for fracture characterization, modeling, and upscaling, and PrimaFlow, which is a multi-purpose fluid flow simulator with particularly good physics for dual porosity. And these tools are fully compatible with any other tools on the market. This slide briefly shows the experience we have in naturally fractured reservoir studies. It's not an exhaustive list, but it gives you a sense of where we have worked. So you will find here all of the main producing regions of the world, and more importantly, all of the different types of contexts. You will find basement reservoirs in the East Asia. You will find the giant carbonate fields of the Middle East. You will find the giant clastic fields in North Africa, for instance. So in these studies, we cover the entire spectrum of possibilities of fractured reservoirs, different lithologies, as I described, different fracture scales from the giant corridors of the Middle East to very, very tiny fractures in coal bed methane, for instance. We also studied complicated fields from a structural point of view, either in the Zagros Mountains or, for instance, in the Andes in South America. So this experience gives us a full confidence in studying any kind of fractured reservoir in the world. The workflow and tools we developed for these particular objects are the following. In terms of the workflow, the question we have to solve is how to model the fractured reservoirs. In other words, how to define the fracture properties that have to be taken into account in flow simulations to build robust production forecasts. So that's the end step of the workflow that we have developed. And this workflow starts with the characterization phase, or if you want, the understanding phase. And this is where you find the idea of the integration that I mentioned earlier. We have the geological data, the image logs, of course, the logs. We have the seismic, sometimes outcrops, geomechanics. And of course, we have all of the dynamic data, production, well tests, flow meters, pressure, all of this at our disposal. And we integrate this data together to, at the same time, characterize the types, scales of fractures involved, their distribution controlling parameters, which could be, for instance, lithology, and their flow impact. For instance, the fractures you see in the image logs, they are compared with the flow meter logs in the same well in order to see what is the impact of these fractures, family by family, defined by their orientation, for instance, on the fluid flow. Same with the seismic that provides the largest fracture component, the faults and fracture corridors. We compare this information with the well information to make sure that there is consistency between the two approaches when wells cross-cut faults seen on the seismic. So here, in this first step, we define a conceptual model that includes all of the fractures that have a role on production in the field, their organization, distribution, and controlling parameters. Once we have developed this understanding, we turn it into a discrete fracture network model of the reservoir. You recognize the different scales and families of fractures on the picture. And we have this unique stage of calibration, unique because some competitors make a priori hypotheses on fracture aperture or conductivity. This should not be done, and this is not what we do. We calibrate the model that we build against the dynamic response of the reservoir. either the permeability interpreted from well tests or the flow meter signature. And this calibration allows to assess the values of conductivity, impermeability, and aperture, for the different fracture families in the model. Once we have this, we have the correct architecture of the model and the flow properties. We are ready to compute the fracture properties in the cells of the reservoir grid. Fracture properties are permeability tensor, the matrix block sizes, which means basically the average fracture spacing in the 3 directions, and the fracture porosity. It's the same way as we do when we upscale the matrix properties. And then we are ready to directly input these properties in a full field simulation, either in a dual porosity formulation or a single equivalent porosity formulation when combined with matrix. So this workflow is at the same time flexible. It relies on a varied amount of data. We could carry it out with limited data, with lots of data. In any case, we will be able to complete the workflow. And it's evolutive through time, meaning that it's easy to incorporate new data and update the model through this workflow. The tools associated with the workflow that I already mentioned briefly, FracAflow is our key solution to input all of the data available from seismic, geology, reservoir engineering to get an understanding of the fractures, their distribution, controlling parameters, and flow impact. With this, we build a fracture model and we upscale it. So everything that I just mentioned is carried out in FracAflow, from the import, analysis, modeling to the upscaling. And this tool allows to integrate all kinds of data and interpret this data together in a comprehensive platform. And our second tool is PumaFlow, which is a flow simulator, particularly good for dual porosity situations, but not only. It has many other specificities like EOR, chemical, thermal. You see, for instance, here, the H2S emission prediction for a SAGD project based on the propagation of the heat in a steam chamber, for instance. So these tools, as I mentioned again, are fully compatible with any other tools on the market. But for us, there are very strong technical solutions built on 30 years of research at the IFPEN. We have here a best-in-class physics for our simulation. At the end of a study, the impact is major for the client. At the exploration stage, we limit the risk of drilling new wells by designing the well path in order to intersect a maximum of fractures when you expect production from fractures in tight environments. And at the field development stage, we identify the fracture role on oil and water gas production. And that's very important because we can contain a production of water and gas that we don't want to produce. And we can optimize the number of required wells to recover the oil in an oil reservoir. And very importantly, we can design the most appropriate recovery methods to increase the reserves, because as you remember, we have specific physics. So we have to understand what is the mechanism for the optimal production of the feeds. I will now illustrate this with a brief case study on a very striking example. It's a giant carbonate field in Mexico with very complex, highly fractured and vuggy matrix. This field started producing in 1979, was put under nitrogen injection in 2000, and it's a giant field that produced up to 2.2 million barrels per day in 2003. And 2003 is the year where we were commissioned to carry out a redevelopment study involving the geological model, the simulation model in order to produce accurate history matching of the production data, and robust production forecasts in order to design a future development strategy of the field. And what you see here, we have the years, the production, the history is in purple, and you see production increase up to 2.2 million barrels per day, more or less in 2003. And the vision of the client at that time was a production plateau about 6-7 years, and then a limited progressive decline. We carried out the study. We started at that time, 2003, ended up at the end of 2004. We produced several scenarios because there was some uncertainty, and these scenarios all describe the same tendency: a short production plateau, a very rapid production decline, and stabilization at a rate around 200,000 to 300,000 barrels per day. So a completely different vision. And what happened actually was that the correct vision that we had by understanding the physics proved true very rapidly, because we observed the production decline as we had predicted. And this consistency and this robustness of the predictions was acquired through the good understanding of the major fracture impact on production. So we have very highly permeable fractures full of oil that produce at a very high rate, but are very rapidly depleted because the matrix is quite tight and the recharge of the fracture system by the matrix is slow. So producing at a very high rate at the top of the structure rapidly depleted the fractures. And at the end of this early production stage, the oil in the fracture system was only located at the base of the reservoir. And this is why we recommended a change in the production strategy by targeting the basal oil column with adequate production rates. So here it's an example of the impact of correctly understanding the physics. And this is done through this integrated effort that I have just presented. I thank you very much for your attention. I hope you liked this presentation, and I really hope that we'll meet in the near future.